let's look at calculating the pH of a salt solution. In the last video, we were kind of mentioning sodium acetate to be a slightly basic solution. Sodium's a spectator, so we're going to kind of ignore the sodium. Sodium has no acid-base properties whatsoever. He cannot increase the hydrogen concentration. He cannot decrease the hydrogen concentration. Acetate, however, does have the ability to remove hydrogen from the solution. It's the conjugate base of a weak acid. Conjugate bases of weak acids are pretty good bases. Where's he going to get the hydrogen from? The water. That's the only particle in the solution besides sodium ions and acetate ions. There's water molecules. So water will be the source of hydrogen. I think the hardest thing about getting these equations started is really just like writing the balanced equation. Now often they'll give you these equations. We want to start with acetate, our base. The acetate ion, C2H3O2. And his source of hydrogen, water molecules. Then we just have to understand what it means to be a base. If that acetate ion is acting like a base, he's going to remove hydrogen from the water. So we will be left with this guy, the hydrogen acetate molecule. And then all that's left of water is just OH, hydroxide. Okay, so we're going to set up an ice table. ICE with our initial molarity being 0.4. That sodium acetate is a strong electrolyte. It will dissociate completely because all sodium compounds are 100% soluble. So we will have 0.4 moles of acetate ions. We don't care about the water. I mean, it's important to put water in our equation because water is the source of hydrogen. And on the product side, I'm very concerned about the amount of hydroxide in the solution. We're just not going to use the water in our equilibrium expression. Initially then, we'll put these two products as 0. And so we know it has to shift forward by x plus x plus x. So at equilibrium, this will be 0.4 minus x, x, and x. Okay, so we just have to solve for x, right? Now, in the last video, we calculated Kb. Originally, they're probably going to do something like this, where they'll say, hey, by the way, the Ka for acetic acid is 1.8 times 10 to the negative fifth. Or maybe in the homework, they'll tell you, like, hey, look it up on a chart. You're not going to find a chart with a Kb value for acetate. This is the best you can do. You'll find Ka for acetic acid, but then we can calculate Kb. Ka times Kb is always 10 to the negative 14th. So we did that already. Our Kb for the acetate ion, 5.56 times 10 to the negative 10th. Okay, so we got that. We already did it. Kb is 5.56 times 10 to the negative 10th. That equals then, is it okay if I just say x squared over 0.4 minus x? Are you getting comfortable with these acid-base ice tables? They're usually pretty common that you'll have x squared on the top and then whatever your reactants are on the bottom. Those K values are, again, very small. This one is ridiculously small that we can almost always 5% rule, right? That should save us from using the quadratic, which is a good thing. So we'll have to cross multiply and take the square root. So 5.56 times 10 to the negative 10 times 0.4, and then I need the square root. X is 1.49 times 10 to the negative fifth. Perfect. And now, do I check the 5% rule? In my head, I am. 5% rule. Check. I mean, I just want to make sure x is small. It's very small. So that if I were to take 0.4 minus x, it doesn't change by more than 5%. In my initial calculation, I just assumed the concentration was 0.4. That whatever X was, it was going to be so small that it's probably almost insignificant. And I do get a small X value. They would not differ by more than 5%. And again, you'll never need to use the quadratic on the AP test. So the 5% rule is a sure thing. Okay, so now I have X, and what do I want to do with it? We want to calculate the pH of the solution. Okay, so look at our particles on the product side. We have acetic acid. That's a weak acid. I have hydroxide, sign of a strong base. When I'm looking at these two, I ask myself, who's going to have a more significant effect on the pH? The answer, this guy. I'm really concerned about the amount of hydroxide in the solution because, again, 99% of those acetic acid molecules stay neutral hydrogen acetate molecules. Will one or two dissociate and form a little bit of hydrogen? Sure. But the amount is so small that, between these two particles, the one that really has a stronger effect on the pH is that straight up hydroxide. We can ignore the amount of acetic acid molecules because, again, 99% of them stay neutral. Okay, so now this really just becomes like the pH of a weak base. Best option, maybe the most common option, I think people are usually going POH equals opposite law of the hydroxide, which is X, 1.49 times 10 to the negative fifth. There's my hydroxide concentration. So we plug that in. And I get about 4.8, 4.83, somewhere in there. And that's super easy. All I have to do is subtract from 14 and get the pH. pH plus POH, 4.83 equals 14. So I got my pH, about 9.17. Slightly basic, which is exactly what we expected. So again, I think the worst part of this whole setup is just getting that original equation. Often they'll give it to you, but maybe not always. So we have to ask ourselves what particles are in the solution and what particles are going to affect the pH. Not the sodium. It was that weak base acetate ion, the conjugate base. Where's his source of hydrogen coming from? The other particle in the beaker is just water. So then we set up this equation just understanding the concept of a base. It should pick up hydrogen from the water. I'm left with a weak acid molecule, acetic, which really doesn't dissociate, so we're going to leave it as neutral molecules. But then I need to know the amount of hydroxide in the solution. Just what we expected. This should be slightly basic. Okay, so these really aren't too miserable. Let's try one more. Let's make sure we got this down. Calculate the pH of a 0.3 molar sodium fluoride solution. The Ka value for hydrofluoric acid is 7.2 times 10 to the negative fourth. Again, very common. If I wasn't sure, now I know hydrofluoric is weak because that K value is small, 10 to the negative fourth. So again, in a solution, the particles present will be sodium ions, fluorine ions, and water molecules. Like we've always said, sodium is a spectator. Anything with sodium is aqueous, so this is a strong electrolyte. It dissociates 100%. But the sodium cannot increase the hydrogen concentration, and sodium cannot decrease the hydrogen concentration. He is purely a spectator. I'm concerned with the fluorine. Fluorine is the conjugate base of the weak acid hydrofluoric. Conjugate bases of weak acids are pretty good bases because, again, they really do have a tendency to pick up hydrogen. Most of the molecules in an HF solution are neutral HF molecules. So again, we have to write this equation. We're going to write it with our weak base. His source of hydrogen will be the water. So then on the product side, we will form hydrofluoric acid molecules, but maybe the more concerning particle will be the hydroxide coming from water. So very similar to the last one. I'm going to have a weak acid, but I'm also going to have strong base. The pH of the solution will be more dependent on the amount of hydroxide. So we set up our ice table. ICE. The initial concentration will be 0.3 molar. We can scratch the water, but I do need it in my equation. My products are 0. I have to shift forward. Minus x plus x and up by x. So that at equilibrium, we're looking at 0.3 minus x, x, and x. Again, like these ice tables become second nature. I mean, they're very, very similar. The only bummer with this one now is that I have the Ka, which again is very common. We have Ka for hydrofluoric, but we need Kb for the fluorine ion. So piece of cake. Ka is 7.2 times 10 to the negative 4th. We want Kb. The product is always 1.0 times 10 to the negative 14th. So we plug her in, and away we go. We got Kb. Kb is approximately, I don't know, about like 1.4 times 10 to the negative 11th. Excellent. Now we can set up the Kb expression. Products over reactants, not including the water. So again, most of us are probably just going x squared on the top. And then on the bottom, we'll have the 0.3 minus x. That K value is crazy small, so we're going to use the 5% rule to cross multiply. So I got 1.4 times 10 to the negative 11th times 0.3. And then I'm going to take the square root. Square root. Okay. So if we go about, I don't know, maybe 2 sig figs-ish, x is about 2.0 times 10 to the negative 6th. Did I check the 5% rule? In my head. X is small, and that's all I'm concerned with. If x is really small, then I know that it's really not going to differ by the original by more than 5%. Okay, so just like we did in the last one, now between these two products, the one that I'm concerned with is hydroxide. Yes, I'm going to form a little bit of weak acid, but 99% of those molecules stay together. So I really don't form a significant amount of hydrogen from the HF dissociating. But I've got these free-floating hydroxide ions. That's going to affect my pH. Okay, so just like the last one, I think most commonly people will just do POH. POH should be opposite log of the hydroxide concentration. POH, which is X, opposite log of about 2.0 times 10 to the negative 6. That was my hydroxide ion. And I get about, I don't know, like 5.7 for my POH. And then all we got to do is subtract from 14. pH plus POH equals 14. My pH equals, how about 8.3? And again, just like what I expected, slightly basic. 99% of this problem is just a weak base problem. The only bummer is that you have to kind of set up the new equation using the conjugate base in water. And then the only other extra step is just right in here. We're given Ka for the original weak acid. We have to switch that to Kb for the conjugate base. But then the rest of this is really just like any other weak base equilibrium problem.